At its core, the system consists of approximately 800,000 human neurons derived from induced pluripotent stem cells. These neurons are cultivated in a controlled environment and are spread across a grid of microelectrodes embedded in silicon hardware. These electrodes do not merely serve as passive sensors, but act as interactive points through which the neuron clusters receive and transmit information. This bioelectronic interface allows the system to emulate feedback loops found in living nervous systems, leading to measurable responses that reflect an ongoing adaptation process. Unlike traditional computers that execute deterministic operations based on pre-programmed instructions, the CL1 learns through a form of reinforcement. In experiments, researchers have provided positive and negative stimuli to the neuron network based on how well it performed a task, such as tracking a moving object or selecting between different inputs. These signals influence synaptic behavior, causing changes in the network that improve performance over time. What makes this particularly revolutionary is that the learning is not imposed through software algorithms alone, but emerges from the inherent plasticity of living neurons. The system is not stimulating a brain. It is functioning, albeit limited, neural substance capable of genuine learning and memory formation during its operational lifespan. The physical design of the CL1 reflects the hybrid nature of its biology and electronics. The entire unit contains a life support system that maintains the viability of the neuron culture. This includes nutrient circulation systems, temperature control, gas exchange mechanisms, and fluid dynamics that mimic the conditions neurons would require in a biological brain. This life support element operates continuously, much like an artificial organ, ensuring that the cells remain active for as long as 6 months. During this time, the system is capable of undergoing continuous interaction, learning, and experimentation, making it a unique platform for neuroscience and biotechnology research. One of the most compelling applications for the CL1 is the field of drug discovery and pharmacological testing. Because the machine contains real human neurons, it can be used to study the effects of various compounds in a way that is much closer to actual human physiology than rodent models or traditional cell cultures. For example, researchers can expose the neuron to a potential medication and observe how it affects firing patterns, signal latency, network structure, and learning capacity. This not only accelerates the testing process, but can reduce the cost of ethical concerns associated with animal testing. Furthermore, it allows for a more precise modeling of neurological disorders, offering insights into diseases like epilepsy, Parkinson's, and Alzheimer's, but observing how diseased neurons behave in real life or real time within a living circuit. From a computational perspective, the CL1 represents an extremely energy-efficient model of information processing. Traditional supercomputers and artificial intelligence systems often consume enormous amounts of electricity to perform even basic tasks. In contrast, biological neurons operate in a vastly lower power threshold. The CL1 consumes less than 1 kilowatt of energy during operation, yet it is capable of performing tasks that require learning, pattern recognition, and adaptation, which are traditionally the domain of high complexity software. This efficiency stems from the fact that neuron communication using brief electrical impulses and modify their behavior through structural and chemical changes, rather than through external processing cycles or clock speeds. Although the technology is currently in its infancy, Cortical Labs has in two no Cortical Labs made the CL1 available to research institutions and private organizations in two formats. The first is a physical unit that can be installed on site, complete with all life supporting and operating systems included. The second is a cloud-based platform where servers can rent access to a CL1 instance remotely. This wetware as a service model is expected to demonstrate access to biological computing, allowing labs around the world to conduct experiments and run machine learning tests on real neurons without the need to maintain the biological infrastructure themselves. To manage this hybrid hardware, Cortical Labs developed a proprietary operating system called BIOS, BIOS. Unlike traditional operation systems, BIOS does not interface only with silicon, but also interprets the transmissions signals to biological neural networks. It transmits digital instructions into electrochemical stimuli and collects neural instructions or neural responses, integrating these into a feedback system that can be logged, analyzed, and refined. The result is a dynamic and interactive interaction between code and biology, enabling researchers to program the neural activity in ways that are still being defined and expanded. In this sense, BIOS acts as a new kind of language bridge between the digital and the organic realms. The implications of such a machine extend beyond computational and biological processing information, forming networks, and adapting to stimuli. Some enthusiasts have raised concern, or enthusiasts, some e- in no some ethicists have raised concerns about the potential emergence of rudimentary consciousness or suffering, while Cortical Labs maintains that the CL1 is not conscious and has no capacity for subjective ethical oversight. Organizations involved in research using the CL1 are expected to adhere to strict guidelines, similar to those applied in stem cell and organoid research. These include protocols related to neuron sourcing, experiment consent, and post-use disposal of the biological material. Another set of questions surround the rights and responsibility of synthetic biological systems. If a machine like CL1 were to be scaled to a level where it could mimic higher order functions or possesses memory continuity, would it qualify for new forms of legal or moral consideration? Some ethicists argue that any system capable of learning, adapting,